Hello and welcome to ChainRule, digging a little bit deeper into some of the advanced applications of derivatives. So basically the idea here is that we want to think about all the things we know about the composition function, which is a function within a function, and see if we can use that to make some of our derivative work a little bit easier. The key to understanding this is to realize that fractions can actually work together. So dy dx is our classic derivative statement. As it so happens, if you sneak a du into the top and bottom, which algebraically I'm allowed to do because I'm keeping the balance, then I create this multiplication problem. It's dy du, which is the derivative of the y equals equation with respect to u, times du dx, the derivative of the u equals equation with respect to x. Once you get good at realizing how these fractions work, it can take a really hard problem and turn it into two easier problems. So what's this going to look like? Well, we've got y equals with a u in it, which is good because it's exactly what we were looking for. Sorry, trying to find the right pen color. So we saw on the last slide that dy dx is the same thing as dy du times du dx. So dy du is the derivative of this guy with respect to u, which would just be 3. And then du dx is the derivative of this guy with respect to x, which would just be 4. So my answer is 12. Now if you want, you could just do basic substitution and say u equals 4x plus 1, so the original y was 3 times 4x plus 1, or 12x plus 3, so my y prime, or dy dx, is 12. So you see that the answers match. It's just a different way of approaching it. Typically, actually, we do the exact opposite in a problem. We see this parenthesis that's too ugly, and we use that to split it up into y equals and u equals. So let's try this out. It's very, very rare that I will offer you a y equals and a u equals in the original setup. The vast majority of the time, you have to pick the u to make the problem work. If the problem hits a dead end, pick a different u. There's a very short list of options. Pro tip is that u likes to be in the parentheses. There's 2 pro tips with u. We'll get to the second one later in the course. But right now we've got our pro tip. So if you're stumped and you have no idea what to pick for u, I would suggest the stuff inside the parentheses. So that's my u, and my du dx is going to equal 10x. And my original problem is now y equals u squared. Now that it's y equals u squared, we go from this horrible problem that I'd have to write side by side, FOIL it all out, and go through all that work, to just taking the derivative of u squared. Once you pick the right u, the problem should be easy to take the derivative. So my dy du is going to be 2u, but my dy dx is 2u times this 10x. Because that's my dy du, that's my du dx. All I have to do to finish this problem is trade back that u that I completely made up. I shouldn't leave u in the answer because I totally just made that up out of thin air. That's my solution. If I wanted to, I could say 2 times 10 to make 20 and distribute that in. But that's my answer. Alright, so the chain rule. Basically, it's your plan B. Whenever the original problem looks too ugly where a product rule or a quotient rule won't do, that's where the chain rule swoops in for the big win. The chain rule is excellent at dealing with really complicated equations. If you can think about the function as being a function within a function, that's where chain rule excels. So if we were to do this old school, you'd have to write x squared plus 1 5 times all out in a row, FOIL them all together, get one big polynomial, and then power rule down the line. Even with Pascal's triangle, it's not going to be fun. With the chain rule, you can say u equals x squared plus 1, and my du dx is 2x. Then my f of x is going to equal u to the 5th. Same thing as y. So it means my derivative is going to be the derivative of u to the 5th, which is just 5u to the 4th, times the derivative of u, which is going to be 2x. It's pretty good. All we have to do is trade back that u that I made up, and you get an answer. Again, you're welcome to say 5 times 2 is 10x. and put that out front. I would not suggest foiling this all out, because that's what we were trying to avoid. And that's our answer. All right, outside-inside rule. This is really just an alternative approach to the chain rule. After this class, I will refer to this outside-inside rule just as the chain rule. It's the exact same rule, just a different approach. As you get stronger at the chain rule, you might find yourself using this technique a little more often, because it's a little quicker in the long run. Basically, the idea is if you can recognize the function as an outside function and an inside function. So it's f of g of. So in our last problem, our inside function was x squared plus 1, and our outside function was something to the fifth. So to the fifth is f, x squared plus 1 is g. Then when you go to write your answer, you can take the derivative of the outside, leaving the inside untouched. The derivative of the outside is power rule. You bring the 5 out front, inside's untouched, and you drop the exponent down to 4. Follow that with the derivative of the inside, which is just going to be 2x. So it's a little quicker as you go to set it all up, but it's also a little bit crazier because you're not documenting all of your steps. So probably within like 2 or 3 days, you're going to find yourself doing this more often, but you have your choice for the entire course. You can always do the formal chain rule if you want. All right, so let's practice outside-inside. So this one's a little bit harder to spot what my u is. I'm going to rewrite the problem to exaggerate that parenthesis. If the parenthesis is not there, maybe rewriting the problem can help you find it. So this something to the 1/2 is my f. The derivative of something to the 1/2 is 1/2 something to the negative 1/2, just as if I do with power rule. But I keep the inside untouched, and then I want to follow that with the derivative of the inside. The derivative of the inside is 2x, and that's my answer. Note that this also helps us replace Noah's rule, because now that we've got this squared on the inside, you can't use the regular normal trick, so instead we have to use the chain rule to answer that question. All right, sine squared x. It would be tempting to let your u just be x, because that's the thing in the parentheses. U is never x. Because if u is x, then we don't need chain rule at all, and we could just do the problem. So instead, rewriting the problem a little bit, you could write this as sine x squared. This is the longer way of writing it, but it's easier to see the chain rule. So if we use outside-inside again, this outside function is squared. So I'm going to say 2 times stuff untouched to the first, and then I want to follow that with the derivative of the inside. The derivative of sine is just going to be cosine, and that's my answer. If you prefer, you could say u equals sine x, and then y equals u squared, and then do the formal way from there. So again, the parentheses are not very obvious. This one's not immediately going to jump at you, but remember, the 5x is inside the parentheses. So your u is 5x. Personally, whether I'm going inside-outside or the traditional chain, I find it helpful just to kind of anchor my thinking by saying u equals, just so I formally state that to keep myself organized. So now we can say 4 secant u, the derivative of 4 secant u is going to be 4 secant of u, tan of u. You actually write it twice. Even though you write it twice, there's still only one u prime out back, and that's just 5. So again, I can say 5 times 4 is 20, if I want. All points on the graph at which the tangent line is horizontal. So this is a throwback to chapter 2. Tangent line is horizontal means the first derivative equals 0. So I want my f prime to equal the derivative of 2 sine is just 2 cosine. No chain rule necessary. Sine squared, we used to have to do a product rule there, sine x times sine x. But now that we've got chain rule, we can just say that's 2 sine x cosine x. If you want to set that equal to 0, the algebra here is far more difficult than the calculus. To try and set trig equal to 0 is pretty annoying. If this was 2x squared plus 2x equals 0, you'd have no problem doing that, but trig makes it harder. In fact, we use the same trick. Factor out your GCF, and then we want to set each one of these groups equal to 0. Cosine is going to be equal to 0 at pi over 2 or 3 pi over 2. That's where I have a cosine of 0. basically straight up on the unit circle and straight down. This guy, when I set it equal to 0, I'm going to get minus 1, and then divide by 2. So I want a sine of negative 1/2. Your best bet here is to think about reference triangles, and that's going to be down 1, hypotenuse of 2. And if you do a Pythagorean theorem, you can find that guy, and then you find that's 30 degrees, or pi over 6. So you've got a full pi plus pi over 6, which is going to be 7 pi over 6. And then you've also got a pi over 6 short of a full circle. So it's going to be 11 pi over 6. All 4 of those are my answer. And that's just if I assume that I'm working within a regular 0 to 2 pi. If I open it up to everywhere, I'd have to add plus or minus 2 pi n for each one of these 4 answers. Alright, so scary word problem. Blah, 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 blah. Equation, blah, 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 blah. Find the velocity of the particle after t seconds. So I'm starting with position. And we know that velocity is the derivative of position. Derivative of 10 is just 0. 1/4 sine of stuff is going to be 1/4 cosine of stuff times the derivative of that stuff. The derivative of 10t pi is a little complicated, but t is my variable. So 10 pi just acts as my coefficient. So I just get a 10 pi in there. If I want, I can combine the 1/4 with the 10 and clean it up a little bit. So whether you're still doing the formal chain rule, and you're saying y equals 1/4 sine of u, and then u equals 10t pi, and going formally from there and finding your y prime equals and your u prime equals, you can go that route. Or you can do the outside-inside to speed it up a little bit. This is day 1 of chain rule. We're going to do a second day because they get a little weirder and the problems can get a little more complicated. And like we saw with product and quotient, you might actually eventually get to the point where you're doing a chain within a chain. All right, enjoy.